Our opening speaker is Snijders, and I think even though we're 8 minutes ahead of time, rather than having me speak on, we should probably make a start. Thank you.
Thank you.
So Tom is based both at the University of Groningen and the University of Oxford. He's been contributing for many years for continuous and discrete time models of network actors, and he's speaking about continuous time statistical models for network panel data.
Okay, thank you. Well, so I've got the honor to be the first male speaker here, and well, that's something, and I'm happy to see that in general, well, I did some counting and guessing about sexes, and so I thought it was about half the male-female ratio for the speakers, so I think that's a good thing, and well, thank you for having me. I will be talking about what the title says, continuous time statistical models for network panel data, and specifically the overview of what I'm going to say is I will first give the general introduction of the model for network panel data, which is not new at all, so I've been working on this for 15 years or so, more than. And some of you know this, but I think a lot of you don't know this, so I will explain it from scratch, more or less. I will give an example, and then I will go on with co-evolution models, which are models where you have not one network, but several networks or networks and nodal characteristics of the nodes in the network. And there, so I will say about a bit of current work about the generalized method of moments, this GMOM thing over there. And I hope I will utilize my 8 minutes extra in a proper way. Let me start with giving you an impression of the type of data that this methodology is concerned with. And this was one of the data sets which has been inspiring me for from the start, really. No, not really from the start, but for many years. And one of the issues is that it's, well, on the one side, precisely the type of data that this method was designed for, and the other side, it's really a very carefully collected data set, and by working over the years with a variety of data sets, I've been impressed by the fact that sometimes some data sets really are very nice, and so they have been collected very carefully. Other data sets are much more sloppy, and so those are also much more difficult to work with. This was a data set in a school setting, secondary school in Glasgow. 3 yearly waves. So at 3 occasions, separated by approximately 1 year, the researchers went in the school and asked all pupils in a certain cohort to mention their friends, and a number of other behavioral characteristics. The purpose of this study was smoking, trying to reduce smoking. That was well, it was research about smoke, but the aim why it was funded was the concern with teenagers smoking too much. This is a picture of wave 1. These are the 129 pupils who were present at all waves. The circles are the girls and the squares are the boys, and the colors indicate smoking and drinking, blue being low and orange being high. And this was wave 1, this was wave 2, and this was wave 3. You see that some of the nodes get bigger. It turned out that at some moment during in the process that we've gone through analyzing it, that pocket money available turned out to be an important one of the determining covariates for the networks, the network dynamics. And there was no measure of social economic status, which is often used by sociologists, but pocket money available perhaps was a proxy for social economic status anyway, you see that some of the kids really get a lot more pocket money as the years go by, and you see that there is a large social inequality. Some have a lot of pocket money, others have little pocket money. So this is the type of data, a changing network on a fixed set of nodes, covariates, so drinking, smoking, nodal covariates, and there were many more covariates. And then the question is how to model the network dynamics and how to model the dependence between the network, the friendship network on the one side, and the behavioral characteristics like drinking and smoking at the other side. Now, this is panel data, so it was at 3 moments the researchers went into the group and collected these data. Of course, between the moments of observation, change goes on. So it is natural to make a probability model which operates in continuous time, or which operates at the very least with changes in between. And I found that the continuous time model was more useful than some kind of discrete time models. So I will be, that is why I will, for whatever reason, for the rest, explain to you a continuous time model with discrete time observations, like here the 3 observations. Already in 1977, the statistician Paul Holland and the sociologist Sam Leinhardt proposed a continuous time Markov chain model for discrete time observations on social networks. And what they proposed moreover was, in this continuous time model, to have changes only occur one by one. So at every time point you can have no more than one change of a tie variable. That means you decompose the change model into its smallest constituents. So what you have to do basically is make a model for a single tie change, which evidently is much more simple than a model for multiple tie changes at the same time. But since you have the current state of the network as the material, the state of the system, the material to define the probabilities for this change, of course you can have a very rich model. What you don't model is coordination between actors. When I speak for an audience of sociologists, and also today, the example I give is that what is not modeled is people meeting each other and falling in love at first sight, because that would mean a coordinated change of a tie at the same moment. Those type of things are excluded. The general approach of continuous time models for discrete time data is also, it's a somewhat minor stream of research, but it is a research since the 1980s at least, 1970s, 1980s, and Kalbfleisch and Lawless in a JASA paper in, I believe, somewhere in the 1980s had an important paper about that. In economics, Bergström worked on it. Currently, still Singer in Germany is working on it. So there is a little niche in the non-network world also for using continuous time models for discrete time data. When I say panel data, it's the same as discrete time data. I just want to say that this exists. I'm not going to talk more about it. The whole operation of the statistical inference is based on simulation of the model, and the heuristic of the model is a so-called actor-oriented perspective, where the nodes in the network, the pupils in this example, are the social actors who choose their ties, and then so it's a directed network. The direction is from the person who was the respondent in this example data set to the nominated person. And so the heuristic idea is that the social actors in the network control their outgoing ties. So they can decide to whom they send the tie. And there is an alternative class of models which also are continuous time models for network dynamics, which is tie-oriented. Tie-oriented in the ERGM exponential random graph tradition, where the basis is of the heuristic is that you've got a tie variable, and that at random time moments there is a decision being taken about whether this tie variable will change from 1 to 0 or from 0 to 1. But the model I will be explaining is this actor-oriented model.
So are the ties the edges? Just
the ties are the edges, yes. When I say tie, I mean the same as directed edge.
right,
Yes.
right. Okay, thank you.
And when I say tie variable, I mean the random variable that is 0 or 1 depending on whether the tie exists.
Is it hard to modify it so that the ties would be a continuous variable, so indicating structure ties, or?
Yes, it would be hard to, and the whole machinery is set up on a discrete outcome space. And currently, one of my PhD students, Nienke Niesink, who is sitting there and who has a poster, so you can read her poster, is elaborate. So I have here, where is the pointer here? So there is this model which I will talk about for network and behavior, which are nodal characteristics, and Nienke is extending the nodal characteristic part to continuous variables, which operates by a model of stochastic differential equations. In principle, it might be possible also to extend that for the network, but then one of the main things also is to reflect about what are the how the network dependencies can be translated to continuous variables, and the network dependencies, like there is some work, and Pavel Krivitsky, who is sitting here, also has done that, but I believe mainly for discrete discrete values, but more than binary values.
So
but
you have something like the number of texts going back and forth.
Yeah. No,
right?
So in principle, it's possible, but I think it's a lot of work, and so Nienke is doing it for the behavior part. And we've got so there's an R package, R Sienna, of which I'm the maintainer, and which is in continuous work. And so I have a website for it where I try to keep track of publications, and we've got I don't know by now about 200 or so published applications. So it's at some moment I took the step to put this out in the open and let it open to applied researchers, and that has worked. The notation is that we've got n actors, and so to fix your thinking, in the application I mentioned there were 160 actors, and so this is a methodology that will work up to a couple of hundred actors, and I can discuss what are the limitations, why I don't dare to advise doing this for 10,000 nodes or so. X is the array of ties between them, the tie variables. Xij is the tie variable. And then there can be covariates. The covariates can be characteristics of actors or characteristics of pairs of actors. Pairs of actors we mentioned we call dyadic covariates. There will be a continuous time parameter t and observations moments I t1 to tm. So the minimum is that you've got 2 observation moments. So already for 2 I call it a longitudinal study.
So the covariates are also discrete?
No, covariates can be anything. The assumption is that it's a Markov process. And of course, when you use more covariates or when you use a richer state space like a multivariate network, then the plausibility of that assumption can be enhanced. One of the fundamental things is that I condition on the first observation, and I do not model the first observation. And of course, in a Markov framework, that makes it easy, because if you've got the probability model and you've got the first observation which you condition on, then you've got the joint probability distribution of everything that happens afterwards. And modeling the first observation then is a different cup of tea, which I don't do, which I just keep it conditional.
Yeah. How does it work with your covariate? So you have this x of t, which is a Markov process. Yeah. Just on its own, or is there sort of some interaction between x and t?
No, in the basic, the covariates are external and so are deterministic.
Oh, they're deterministic.
Yeah, but halfway my presentation, I will also mention an example where that is this co-evolution, where you've got other variables that are jointly dependent.
For example, I could think of the covariates, my probability of smoking.
Yeah, exactly.
But you say that is external, so it doesn't depend on my friend smoking.
No, but so halfway in my presentation, I will be treating co-evolution, and then it does depend on there is this mutual dependence. So to give the the precise definition of the model, we've got the continuous time model and a discrete state space, discrete state. At random moments, there is an event occurring, which is that one of the actors gets so-called the opportunity to change a time variable that is sent by this actor. So xij, I is the actor who, so in the heuristic, who makes the step, who makes the decision, changing xij from 0 to 1 or from 1 to 0. This happens at the rate lambda. The rate lambda depends on the actor. And can depend on parameters, can depend on or will depend on parameters, can depend on the state of the network. And the waiting time until the next opportunity for change, this next micro step, has an exponential distribution, and the probability of the actor that is taking the micro step is the ratio of the rate for this actor divided by the sum of the rates of all the actors.
When you assume they're independent, so you have a Poisson process.
Yeah, it's a Poisson. So it's conditionally independent, conditionally given the state, given the current state. Since there are usually only a few waves, we cannot make the model for the timing too rich. So the main model is what is now on the slide, is the probability which is the particular tie that is going to be changed. And that is then represented by what we've called the objective function. Objective in the sense of objective like goal or aim. So the objective for actor I. And so which gives, which defines the probability for going from the current state, which here is x old, to a new state x new. And if x old is constant, then you can think of this like a potential function in terms of x new. And to give those probabilities and to give the equation how the probabilities depend on the objective function, the current state is denoted x, and x plus or minus ij denotes the network where the time variable xij is being toggled from 1 to 0 or 0 to 1. The rest of x plus or minus ij is totally equal to the current x. And then the probability of toggling this particular variable, given that I is the actor that takes the micro step, is this ratio. So you could say that actor I compares the objective function of the network that would obtain after this particular change of the variable I to j with all the other changes that actor I could make, which are those x plus or minus I h. So I is fixed. If you think in terms of the adjacency matrix of the network, then I defines a row of the adjacency matrix, and I chooses one of the elements of the row to toggle.
Now, is it so? Are these independent for each ij, or is it that I choose one and only one out of those? So is this a multinomial or binomial?
This is a multinomial. This is an equation for a multinomial. Yes. And so I is fixed, and and then over the continuous time process, random i's will do this decision one after each other.
And no choice of doing nothing.
Yes, there is a choice of doing nothing.
Which one is that?
That is, well, was it here? That is II, since the diagonal is empty. And the heuristic interpretation is that if I'm satisfied with the current network, then I don't need to change anything. So it's totally straightforward to simulate this model. You generate the time increment, you choose the actor based on the rate functions, then you choose the type to change based on the actor that was chosen and the objective function, you effectuate the changes, and then you start all over again. So this is the principle of the simulation for the Markov chain. Of course, from the point of view of applications, the question is how do you specify this objective function? And the model for the continuous time process, so the model for the probability model, is a generalized linear model. And so we've got a linear predictor here where those SIK of x are, well, you could say the explanatory functions, explanatory statistics for the change at every moment. And we call those functions the effects. So they are statistics on the network as seen from the perspective of actor I. And I will mention a few. A basic statistic is the out degree of actor I. And having the out degree in this model means that the out degree models the balance between creating a tie or dropping a tie. So creating a new tie or dropping an existing tie. And since networks are sparse in practice, the out degree effect almost always will be clearly negative. Then there's a reciprocity effect. So this is the number of reciprocated effects of reciprocated ties for actor I. Since it's an actor-oriented model, so the decisions are decisions by actor I. So everything is about the network as viewed from the perspective of actor I.
So it's a digraph then.
It's a digraph. Yes. It's a digraph. Yes, it's a digraph. So this is the number of reciprocated ties. Then for transitivity, we can model transitivity in various ways. The most simple-minded way, mathematically, is the transitive triplets effect. So the number of transitive triplets in which actor I is involved. So always I will be the focal actor who is the actor making the mini step, making the micro step, who makes the choice. So the number of pairs Hj which have this configuration for actor I.
So in all of these cases, for example, in the triplets, do you compare the number of triplets before and after the suggested change?
Yes. But since the current you can in this equation you could subtract the function for the current change both sides. So it's it's just the same.
Doesn't matter. Good.
Like in exponential random graph modeling, we are not totally satisfied with this transitive triplet count. So in exponential random graph models, working with the transitive triplet count really is almost impossible. That is not so here, but still the same. So in the spirit of the exponential random graph model, here also the number of transitive having a linear function of the triplet count as the explanation in your generalized linear model just is not realistic. And much more realistic is to have something of a decreasing, so a concave function of this. So here you should focus on this. So the number of two-path connection from I to H, H to J, number of two paths connecting actors I and J, and so it doesn't matter what this is precisely, but it's a concave function of the number of two paths connecting I and J. And if you have this, then it's a linear, so just the linear function. And this is a downweighting of larger number of connections, which is empirically often better. And then, of course, we can connect the covariates in various ways. And when we've got actual covariates, then we've got to transform the monadic nodes to the dyadic ties. And that can be done in various ways. I don't want to focus on that. That's a topic in itself. You can have a different parameter for creating and for terminating ties. We will see some of that. We will see an example of that. So I don't go into the details of that, but I just mentioned that there is this possibility of differentiating parameters for creating and maintaining ties. For example, think of the transitivity, friends of friends are friends. You can have, in the real world, we can say that there is a social mechanism of transitivity by introducing people to each other. Because of introduction, transitivity occurs. And introduction, of course, works only for creating ties and does not work for terminating ties. And that is an example why it is conceivable that transitivity works more strongly for creating new ties than for maintaining existing ties. And so that's an example of the social mechanism where those parameters might be distinct. For the rate function, mostly we use, for networks between humans, we use constant rate functions for, like in the example of a friendship network. Mostly we use constant rate functions, everybody making changes at the same rate. However, when we've got several, when we've got more than two waves, more than two observation moments, then we've got more than one period between observation moments. And even though in the example, so the periods were yearly waves with 1 year in between, but the pupils were older, and so perhaps between 13 and 14 they changed their ties more rapidly than between 12 and 13, because at some moment adolescence sets in and puberty sets in, and they are open to the new world of friendship and perhaps girls and boys and so. And so you might conceive that there are more changes when they are 14 than when they are 13. And we have no clue about that. So there is no physical time in the social world. And because of that, even if the process itself, the change probabilities, would be would be constant, so the marginal distribution can change, but in this model the transition probability is constant over time. Then still we don't know whether the periods in between our observations really have the same length with respect to what a social amount of change would be. And therefore we've got three parameters, so the rho m for a multiplicative parameter for the rate of change in a particular period. And I think this is important for applications because it means that you have a separation between your observation scheme and the model which happens out there in the real world. And this rho m are important to separate the observations from the real world process. And we can also make the rate of change depending on actual characteristics or on expositions like their degrees or so. I want to say something about estimation. And if we would have complete time, if we would have complete data about all the changes being made, then it would be a generalized linear model, and then it would be all straightforward. Well, there would be some time heterogeneities, but all would be straightforward. But for panel data, estimation is less straightforward because you've got all these missing data. And we've developed method of moments. We are now working on generalized method of moments. I will explain that. We've also developed Bayes and maximum likelihood estimation routines. The likelihood-based routines are based on a different kind of simulations because they use Metropolis Hastings simulations for estimating the whole process of changes from one observation to the next observation. That is much more time-consuming computationally, so the currently maximum likelihood is implemented in ways that take, I don't know what, perhaps 100 times as long as method of moments. And I will say, I will explain something about the method of moments. So there are papers also about maximum likelihood, but I'm not going to explain those. For the method of moments, or you could also say estimating equations or M estimators, we've got a statistic which has the same dimensionality of the parameter. So for each parameter you could say there is a statistic, and there is a statistic that is sensitive to this parameter, so that the parameter will tend to lead to higher outcomes of this statistic. And the method of moments is defined by this equation. And it's a time-honored estimation procedure. So that's the, and of course it has a kind of direct conceptual appeal that you make a correspondence between your model and your data. The first question is, what statistics do we choose for this model, given that we have only panel data? Suppose that we have a constant rate of change, then for the rate of change it is totally straightforward, the total amount of observed change, so number of ties different between consecutive time moments is a parameter for the rate of change in that period. For the weights in the objective function, it is less straightforward, but still, if you think of it, also quite clear. So I'm here considering objective functions that do not depend on the previous time point, so there is no differentiation between creating and maintaining ties. It's just like, well, so as close as you can get to a potential function. And when we have a larger beta, then it is clear that the actors will be attracted especially to network states where this function SIK is higher. And that will be the case for all I, because all actors are supposed to have the same parameter. So that means that the sum of those SIKs for the later moment, I'm talking now about only 2 waves, the sum of the SIK for the later moment over all actors is the statistic that is sensitive to this parameter beta k. I have tried often, I've sit down to see whether I could prove this, and so intuitively, for me it's totally intuitive that this will be the case, but with these discrete outcome spaces, I think that there may be some parts in the space where it doesn't hold, and so I have not been able to make a proof. But everything that is based on these equations in simulations always works perfectly. But so I am not totally sure that mathematically that this equation always holds. There may be somewhere exceptions. However, intuitively, I think it's totally evident that this is a sensitive statistic. Recall that the model conditions on the initial outcome, so that it is reasonable indeed to let this depend only on the later outcome. The second question, if we've got the statistic, the second question is how to solve the moment equation, because we cannot calculate those expected values. However, we can simulate the process for given provisional parameter values. And then we can use the Robbins-Monroe method for stochastic approximation, which is based on this equation. So you simulate, you've got provisional parameters theta hat n. You simulate the whole process, that gives you an outcome Zn. The observed values are little z, and the deviation between what you simulated and what you observed gives the change to your current provisional value theta hat n. There must be a constant, since this is of course random, there must be a constant that is positive but decreases to 0 in order to let this converge. And for this kind of techniques there has been a wealth of research on, so since 1951, since Robbins and Monroe, this is the same Herbert Robbins, by the way, of the empirical Bayes method, so it's the same Robbins. So there is a lot of tuning to this, but this is the principle of the method. Let me give an example. So for this Glasgow data set, and for the transitive closure, I do not use the transitive triplets, but I use this G-Wesp effect, which I mentioned with the concave function of the two-path connecting I and J. And this is what I would say, this is typically what you get for this kind of data. So this does not yet use a lot of covariates, so I only use sex as a covariate. And of course you could, there are more, you could look more closely at how the network dynamics depends on other covariates. But you've got this whole sequence of what we call structural effects. So effects how the network dynamics depends on the network itself, on the current state of the network. And without giving formulas, let me briefly go through the whole list to tell you what they mean. So rate of change, so 11 and 9 times are the times that actors get an opportunity on average to make a change. And recall, they don't, when they get the opportunity, in the first place, they don't need to make a change. In the second place, they might make a change that later on they retract again, because it's all unobserved. So the actual average number of changes is considerably lower than this 11 and 9.
Is it 11 per year number?
Yes, for each pupil. Yeah, because there is no time, so the time unit is just 1 between waves. The out degree is the balance between creating and dropping ties. Now, given that there are 160 pupils and I'm only 1, so I've got 159 options to change, and the network is sparse. On the average, there are something like 5 or 5.5 ties per actor. So the average degree is between 5 and 6. And that means that I've got many more options to create new ties than to drop existing ties. And that is why the out degree effect is strongly negative. Of course, this is taking into account everything else. Is strongly negative in order to keep the network from growing too much. There is a strong effect of reciprocation. These parameters can be tested approximately by dividing the parameter estimate by its standard error and referring to a standard normal distribution. So when it's about 2, then it's significant at conventional significance levels. So you see that reciprocity, both for creating and for maintaining ties, is strongly significant, but it's more strong for creating than for maintaining ties. The GWESP, that is this transitivity, the transitivity is significant for creating ties, but is not even significant for maintaining ties. In degree popularity, that is the extent to which people with currently a high in degree, so a high number of choices received, are popular, so will be attractive as targets for nominations. That is not so. So those who have more incoming ties at this moment will be somewhat, not very strongly, but somewhat avoided by the others. Those with high out degrees, the out degrees don't matter so much, but the out degrees do matter for the activity. So those who currently make many nominations will tend indeed to continue making many nominations, or making even more, because it is significantly positive. Reciprocated degree activity, you see that is of, so these 4 effects from in degree popularity to reciprocated degree activity are all effects having to do with the number of ties received and sent by the actor. Reciprocated degree is the number of reciprocated ties that an actor currently has. You see that has a parameter of -0.26, strongly significant, significantly negative. And that can be interpreted that when an actor has a lot of reciprocated friendships, then he is not so inclined to enter into more friendships. So he doesn't, because then entering into a new friendship would be a new, potentially non-reciprocated one. So why does he care? Because he already he or she already has a lot of friendships. Sex. So there is. We often see strong sex homophily effect here also, certainly at these younger ages. So this is typical what you get from, so it is totally in the generalized modeling framework, except that you've got this simulation-based estimation. But the whole type of results is in the modeling, generalized modeling framework. that is the basics of the model for one network. Let me now go on to explain the model for co-evolution, where you've got a network and an actor characteristic, like smoking and drinking, that develops in mutual dependence with this network. The whole idea of co-evolution is that we use this framework, but now have several dependent variables that co-evolve jointly. And I will focus on the case where the other dependent variable is an actor variable. As I mentioned at the start, all of this is inscribed in a discrete state framework. So the actor variable also is discrete. We model it here as ordinal discrete with integer values, so that when there is a change, it can move up by an integer or down by an integer. And the idea of this micro step also is applied here. So we model the smallest possible changes. And the smallest possible changes are changes one up or one down. So a micro step for the behavior is a step in which the actor has three options, either changing nothing or moving up one or moving down one. The whole modeling setup that I used for one network now just is multiplied, and so for each of those dependent variable, each behavior variable, each other network potentially that you have, there will be a rate function and an objective function. So for the computer the simulation algorithm works like this. You generate a time increment, then so what is additional to the previous one, you choose the variable that you're going to change, which can be the network or the behavior. Let me call that the behavior, smoking or drinking, whatever. So is it the network or the behavior that's going to change? Then given that you know that, you choose the actor who makes the change. Given that you know the actor and the variable, you choose the time variable that you're going to change, or you choose the behavior change, one up or one down or no change. And that is it. Then you update and then you go on. So this is just the only thing is this step here, this second step in between. In applications, this is so it's very much used to use what sociologists call social influence and social selection. And the one of the basic questions is, okay, we see that smokers tend to be friends also with smokers, and non-smokers tend to be friends also with non-smokers. That's an empirical regularity. That might be caused by smokers selecting smokers as friends, or it might be caused by smokers influencing non-smokers to start smoking, or smokers keeping their smoking friends, so smokers influencing their smoking friends to start smoking, or influencing their smoking friends to keep smoking. So social influence is influencing your friends to do the same as yourself. Social selection in this case is selecting friends on the basis of common behavior. What is it? And of course the real causes, so with these statistical methods you cannot get at the real causes, but you can get information about what happens first and what happens later. So the principle, the heuristic principle, is that each actor controls the outgoing ties, and each actor also controls the behavior, which is totally natural, and that they both evolve in continuous time. So the interdependence between the processes is reflected by the fact that in the objective function, so we've got an objective function for the network, which is this, and that will also depend on the behavior. And we've got an objective function for the behavior, that's this, that will also depend on the network. And so this common state, so to say, defines the mutual dependence between the two processes. The behavior, the microstep for the behavior evidently is distinct from the microstep for the network. It's also a multinomial choice, but for the network we had n options. For the behavior we have only 3 options. The 3 options that I mentioned, -1, 0 or +1 as change. But then we've got the same multinomial probability. Then there is the question for the applications also, how to specify the the objective function for the behavior. I will skip through that and I will say something about estimation. For the estimation, we now have 2 or more of those objective functions with parameters of which we want to estimate the parameter values. However, one difficulty is that for those effects, there might be the same mathematical functions that are being used. So, for example, think about gender and similarity. So think about gender and out degrees and in degrees. If girls are generally more attractive than boys as think of alcohol drinking as the dependent variable. So we've got alcohol drinking potentially in 4 categories from nothing to strong drinking. It might be so that people who drink a lot of alcohol are more popular as friends. That would mean that the sum of out degrees sum of in degrees weighted by amount of alcohol drinking are one of the functions here. But it's also possible that those who have a lot of friends will develop their alcohol drinking more positively. So when they've got a lot of friends, they are going to drink more alcohol. That means that here also the in degrees weighted by alcohol drinking might be a function here. So you could have the same function here and here. Still you want to estimate different parameters. However, there and in the method of moments estimate that I explained you for the network only case, you would think you get the same parameter. However, here we can distinguish, here we can use the time order, because the influence, if we've got social influence of the influence means that the network influences the behavior, so that those with more friends will drink more alcohol. Then we have the network at the earlier time moment and the behavior at the later time moment. Selection means that we have the behavior at the earlier time moment and the network at the later time moment. So the order of the time moments is exactly converse for the influence of the network on the behavior and the network and the influence of the behavior on the network. And that means that for the parameters in the network in the network dynamics, we can use this where the behavior is at the previous time point and the network is at the later time point. In the behavior dynamics, we can use it conversely, the network in the earlier time point and the behavior at the later time point. So in this way, in this co-evolution framework, we still get different statistics for the same mathematical functions as IK, the same effects which are used both in the network and in the behavior objective function. That works nicely, relatively nicely, so when I started this, I didn't know whether it would work, but it works relatively well, but it can be improved. And this improvement is work that we are doing now, and that is, so in this method of moments, you've got equally many statistics as parameters. But of course, you've got more information in the data, so you can use more statistics than parameters. That is called the generalized method of moments. And then what you have to do is you cannot equate the expected value to the observed value, but you can minimize such a quadratic form, such a deviation, for a suitable weight matrix W, and the optimal weight matrix is the inverse of the covariance matrix at the estimate. So there is some estimation to do here to get the optimum.
So what do you say this is the optimum? Under what criteria is it optimum?
It is okay. That's it is optimum for the. Okay. Now I blank on the precise weights for the so expected quadratic loss. So it's a weighted quadratic loss function. And so now, so we had earlier the, sorry, here, what did we have? Yeah, so here we had earlier we had these are called cross-legged functions because you use the opposite legs of the time, so T1 and T2 are used here in opposite ways. And what we use now, we can use the same, so the functions both at the later time moment, which were not used yet. So this is an obvious choice for using also here. Now there is some algorithmic work to be done because we need to minimize this, and then it has the same form, almost the same form as the equation for the Robbins-Monroe. So we had this in the package. We've got this Robbins-Monroe-like algorithm, which is very stable and for which we have a lot of things in place. And so we can use that with some additions, because here you have this matrix B, and if you pre-multiply by this matrix B, which you have to estimate, then again you can use the Robbins-Monroe algorithm to determine the solution of this equation. And again, we want to have this in a package which we send out for use by researchers out there whom we have potentially no contact with, because if they have problems they will come to me, and that's okay, but I want to minimize that. But we are now in the moment that we have in principle a reasonable amount of tuning that this should be close to being put into the open. And the kind of advantage that you get, so this is now a simulation result for a comparison between the regular method of moments here, MOM, and the generalized method of moments here. And you see, so this is, well, a typical simulation set up with a typical model, which I'm not going to explain. And so for the root mean squared error here, So this is for the what I have in red here is for the parameters that depend on the behavior. So this is for the network. Is this for, yes, and the next slide is for the behavior parameters. And for the network, you see here 138, 116, 892, 642. So there is a decrease in root mean squared error. And here also you see that there is a decrease. So it's not enormous, but still it is. There is a decrease in the root mean squared error. So indeed there is an advantage in power for the generalized method of moments. So this is typical the advantage that you can get.
So how do you know that this is actually a reduction in error and not just overfitting?
What do you mean by overfitting?
Well, now that you have sort of, relatively speaking, less parameter and more data, you might have a tendency.
No, but you don't have more data. You use the same data. So you have the same number of parameters. You use your data in a different way, but you've got the same data anyway. So overfitting would be that you use more parameters, but the number of parameters is constant. These simulations were done for a correct model specification. Of course, you never know that the model is correct in practice. And the generalized method of moments might be more vulnerable for model misspecification. However, then looking at the distinction between between the estimates of method of moments and generalized method of moments might then also be used as a model specification diagnostic. That is still something to be further developed. Okay, I'm close to the end. So there is a website and there is a software package. Let me go to the last part and the discussion. So the model is an exponential family with a lot of missing data, generalized linear model with lots of missing data. We use a frequentist, we mainly use a frequentist simulation-based estimation. One of the advantages is that you don't have to specify the prior, but also an advantage is that convergence checking is much more straightforward, so we know about the difficulties of convergence checking of Bayesian MCMC. This is simulation-based, but convergence checking is easier. This method of moments performs quite well for if you've got one dependent network, if you've got more than one dependent network or networks and behavior. As I said, it may be not so efficient, and the generalized method of moments is a hopeful candidate for improvement. We are working on a number of extensions. So I already mentioned the work by Nienke Niesink about continuous dependent actor variables using a stochastic differential equation model. And you can look at her poster at the poster session. And that is my presentation. Thank you.
Well, we've had some questions during the talk, but do we have any more questions?
I was wondering about the precision of the estimates you get out, if given the number of parameters, and you seem to have not so many actors in your data, so many time points. Is it well feasible, this, or do you have standard errors that make, say, these causal conclusions?
It is for data sets that we typically have, like 50 or 200 or 300 actors. You can estimate a lot of parameters for the network quite precisely, but power for the behavior part is quite low. So, and of course for the network you've got much richer data than for the behavior. And that was one of the practical reasons for us to develop this generalized method of moments, because especially on the behavior part, we hope to get more power. And but nevertheless, so with, and of course, it's not always just one network that you have, but more and more social scientists are collecting networks in several groups, and so a typical data set now will be 20 networks of 200 pupils each, if you are talking about school research. Then of course you cannot make the assumption that all parameters will be identical, so there is still something there, but still it is in this field of research about social influence and social selection, with sample sizes that are normal, like the sizes I mentioned, also for social influence, we have reasonable power but not high power.
You do not need sparsity assumptions or penalization or things that you do not need to artificially set parameters to 0 or something. Or
no, well, we do make a model specification, so we do set parameters to 0 for which we think there is no evidence. So we don't use a formal penalization or that has not been developed, or whatever lesser kind of thing, but that is done in practice by a model selection step, where you test parameters, and it will be jointly, in discussions with social scientists, I always say that you need to know, well, social scientists use the word theory, and for me as a mathematician that was very funny to hear theory being used, but still, that is also, so sociological theories also are serious. So you've got to use the sociological theories. However, that is easier said than done, because the social science theories are not so specific that they tell you about this type of model. Still, so the short answer is we use model selection steps where we also put parameters equal to 0.
I mean, the question marks after your point 7, does it mean that you are not sure what is the best asymptotic framework?
The question mark means that there is research to be done, and that so we and under which condition and based on simulations, I think that it works reasonably well, but so there are a lot of questions still, so there is a lot of unknown here.
Yeah, suppose there is a tie from me to you, but not the other way.
Yeah.
In terms of, let's say, alcohol, am I possibly affecting you in terms of drinking alcohol, or you possibly affecting me, or both?
That is up to, that is not pre-specified by the model, but so there are different effects that express all those possibilities. The basic possibility here, so the first that I say social researchers should think of, that if there is a type from you to me, that you would be influenced by me, so that you would have a perception and I would be a socially relevant person to you because you consider me your friend, and then there would be an influence from me to you, because the idea is that friendship nominations indicate people who are relevant for the person who is doing the nominations.
Yeah, I also, if there is a link from me to you, probably you affect me more than the opposite.
Yeah.
And that's allowed in your model.
Yeah, you can see whether it's one or the other, but for that you have even less power. So for those differentiations, power really is very low.
Any more questions? In that case, let's break for coffee and
Okay.
thank our speaker again.